Okay. So if I see anybody online, I'll click admit, but I don't see anybody listed there right now. All right, now, if you can imagine the y coordinate is sine, right? At any point here, say pi over 6 is the angle. The coordinates are cosine pi over 6, sine pi over 6. Right? And we can do that for all the angles. If we put theta versus y equals sine theta. Then when theta is 0, we get y coordinate 0. Theta is pi over 6, we get this coordinate, which remember this is a 30, 60, 90, so this side is 1/2. We put in pi over 4. We get 1 over square root of 2 here. Then pi over 3. Right, this becomes a 30, 60, 90 this way. And the y coordinate is square root of 3 over 2. And at this point, at an angle pi over 2, the coordinates are 0, 1, so the sine is the y coordinate is 1. And then we keep doing that. We go up to 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, a straight angle, and we start coming down these same numbers, right? At 2 pi over 3, we get the same y coordinate we did at pi over 3. 3 pi over 4, we get the same y coordinate we did at pi over 4, and so on. So we get these same numbers going down. And then we have the same coordinates except negative going around this way, right? At 7 pi over 6, the y coordinate is minus 1/2, 1/2 unit down. And so on, now we get the negatives of all these coordinates coming back until we go around to an angle of 2 pi, all the way around, and the sine is 0 again. So I'm going to put et cetera here, and say now we can sketch this graph, right? If we just plot theta versus y equals sine theta, we start at the point 0, 0. We plot the point pi over 6/2. Here's 1, so here's 1/2. Got pi over 4. We've got square root 2 over 2. And so on. Here's pi over 3. We got square root 3 over 2. And at pi over 2, we said we get 1. That's the maximum value. Now it comes down in the same way. There's our special angles. And at pi, we got 0. Then we get negatives of the same coordinates. And if we use the calculator, we can fill in between each of those dots. And the graph of sine looks like that. It plots the angle versus the sine of the angle. It is, after all, a function. It's like if you plot x versus x squared, you get a parabola. When you plot theta versus sine theta, you get this sine wave, we call it. And it goes down in the same way and back up, because when you come down here, the y coordinates is negative what they were up here. Well, we get out here to 2 pi. And there it is. There's y equals the sine of the angle. Now you can imagine we can also graph cosine, right? We didn't discuss that. To graph cosine, now you just plot the corresponding x coordinates right here. So x starts out at 1. Then it goes out to square root 3 over 2, square root 2 over 2, 1/2. The x coordinate's 1/2, and then the x coordinate's 0. We're getting exactly the same coordinates if we plot theta versus the x coordinate, which is cosine theta.
So will those stay the same throughout all of these graphs, the cosine over 6 and sine over 6? Like, will those ever switch like to x or y?
I'm not sure I understand the question. This is the graph of sine theta.
Okay.
And so I only graph the y coordinate on the unit circle. Now, if I graph the cosine theta, then I'll graph the x coordinate. We will do different related graphs. So if we graph, for instance, the graph of y equals sine 2 theta, then it will look different if we look at y equals 4 sine 2 theta. It'll look different. We're gonna do that later today.
So is y always gonna be sine though?
Oh, I see what you're saying.
Yeah, like,
No, the y coordinate I can plot is, yeah, it's either sine, sine or cosine or anything. Yeah, just in this one graph.
okay.
Just in this one graph. In fact, let's write that down here so there's not confusion. Let's plot theta versus cosine theta. It is the x coordinate here I'm gonna put. When theta is 0, I get 1. When theta is pi over 6, I have the x coordinate is square root 3 over 2. When the x coordinate is pi over 4, I've got square root 2 over 2. And theta is pi over 3, the x coordinate is a half. When it's pi over 2, I get 0, not the x coordinate here is 0. And I keep going all the way around to, when I get back to 2 pi, once again, the cosine is back here with x coordinate 1. So this time I plot the x coordinates in the unit circle, but on the graph here, I'm going to graph it as though I'm going to graph y equals cosine theta. And if I graph these points, 0, 1, it starts here now. Pi over 6 square root 3 over 2 is here. And I've got, let's see, pi over 4 square root 2 over 2. And pi over 3, 1/2, pi over 2, 0. And it goes like this. And then cosine of pi, if you take this angle, you get the point -1, 0. So the cosine of pi is -1. And that's as low as it gets. When you got here to pi, cosine reaches a low, -1. You should put that point in here at pi, you get -1 in the cosine. And I'll graph this with the y coordinate being the cosine this time. And I get this graph. This is the graph of y equals cosine theta. Now, if my graph isn't that readable, don't worry. There's lots of high resolution graphics online. I brought the one up from Wikipedia. Wikipedia is a nice place just to look up a brief summary of some of these things. Hopefully you can see the graph, but here's a nice graph. I spread mine out a little more. Theirs aren't scaled the same, right? This is 3 units here in x and 1 unit in y. So it's really spread out more like mine. But if they actually scale differently, then here's the sine goes like this and comes back. Here's the cosine comes down and comes back. And now you see it go off the end. Because you can keep going past an angle of 2 pi, you go around and then keep going. And you repeat the same values for sine and cosine, right? You get the same y values as you go around. So this is going to come up and do the same thing over and over. At 2 pi plus pi over 2, you get the same values you did at pi over 2. So you get this again. So here's 5 pi over 2 is the same as pi over 2, because anytime you add 2 pi to an angle, here's pi over 2 and here's pi over 2 plus 2 pi. You get the same y coordinate. So this is going to repeat every 2 pi units every time you go around the circle. Right? Now what you see is that when this one's at its peak or valley, the other one is crossing the x-axis. And when this one's at its peak or valley,
Professor, are we supposed to see the chalkboard right now? Because we're just looking at the.
Oh, I'm sorry. I switched over on there. Yeah, thank you. There we go.
Thank you.
Yeah, so the graph is going to repeat like this as you go around angles past a whole revolution. By saying that 5 pi over 2 is the same as going around 2 pi and then pi over 2, you get the same y coordinate as you did at pi over 2, so these will match. And every time you're a whole rotation apart, 2 pi radians apart, they get the same value. So we call this graph the sine wave. And if you look carefully, you see exactly the same shape. Well, of course they are, because you just went around this unit circle, which is symmetric. This one's the y coordinates, one the x coordinates. They're just the same curves except shifted. In fact, if you think about it, this is just the cofunction identity. We'll explain that later, but the graphs are exactly the same shape, just shifted over. So we call them both sine waves. Now in practice, you may not get exactly a function y equals sine of theta. You may get something that's a little different. There are lots of related graphs. As an engineer, you never get a current that has exactly a sine wave every 2 pi seconds, right? It's always got a different frequency. And so what you do is this. To sketch related graphs, which is what comes up in practice, y equals a sine bx, where a and b are just numbers that you're given. We can use our algebra strategy. Remember in algebra, the graph of y equals a times f of x, where f is any function whatsoever, is the graph of y equals f of x stretched vertically by a factor absolute value of a and flipped upside down if a is negative. Okay. I just want to illustrate this. If I have y equals x squared, right, the basic graph of algebra, I know by putting in x equals 1, I get y equals 1, I get this point. If I put in x equals minus 1, I get y equals 1, I get this point. If I put in x equals 0, I get y equals 0. Here's 3 important points on it, right? Now, what if I want to graph y equals 2x squared? What does that do? That just doubles every y coordinate on here, right? You put in x equals 1, you get 1 squared times 2. Put in x equals minus 1, minus 1 squared times 2. Everything is doubled. And so each y coordinate is doubled from here, and you get a graph that's twice as tall. So you get the point 1, 2. You get the point minus 1, 2. But the points on the x-axis doubled still stay on the x-axis. You get 0, 0. It doubles every y coordinate. It stretches it like this. Any points down here are twice as far down, right? If they have negative coordinates, it's doubled down here. So it's a stretch by the absolute value of a. And then if I multiply by minus 1, like suppose I want to sketch y equals minus 2x squared. Now it's stretched by a factor of 2, and all the y coordinates become negative, right? So the parabola looks exactly like this one, but right, this graph is just minus this one. You flip this one upside down. Now you got minus 1, minus 2, 1, minus 2, and still 0, 0. So if you know what one graph looks like, you know what a number times that graph looks like just by stretching it by the absolute value of that number and turning it upside down if that number is negative. So this one's twice as tall as the first and flipped upside down. Moreover, the graph of y equals f of bx is the graph of y equals f of x. And what do I have to do that? I should have said on this first one, I said it out loud, but I didn't write all the words. This one was stretched vertically, first one. When I replace x by bx, it's a stretch horizontally. And I said stretch, it can be shrink. If a is a half, then it's half as tall, right? It stretches by a factor of 2, it's twice as tall. So if you multiply by a half, it's half as tall. Same thing here. This is stretched or shrunk. By a factor 1 over absolute value of b in the x coordinates. horizontally, let's say, and flipped over the y-axis if b is negative. Blocking, I guess you can't see there, sorry. All right, and you can see this from a simple graph like the squaring function again. If I have y equals x squared again, and it goes through these three easy points. Now if I replace x by 2x, let's say, and I want to graph y equals 2x squared, so everywhere I see x, I put 2x. Now what happens?
It's horizontally stretched by 2 out.
Yeah, actually
X.
about 1 over 2. Now x only has to be half as big to square the same number. So when x is half as big, you get the same y. If you put in 3x squared, then x only has to be a third big to get the same y. It's that kind of thing. So instead of getting 1, 1, you get the point 1/2 1. X only has to be half as big to get the same y. Right? Same thing here, minus 1/2 1. And it has in this case, it has the same effect as stretching vertically by a factor of 4. But it's really a horizontal stretch in general. So here's a graph of y equals 2x squared. I should make it look like that. And it was half as, there we go. And if I also put in a minus, then it flips it over the x-axis. In this case, it'll flip onto itself because it flips over the y-axis. In this case, it'll flip onto itself because it happens to be symmetric there. All right, so that's what you do if you replace x by bx and graph y equals f of bx. It's a horizontal stretch by 1 over absolute value of b and flip over the y-axis of b is negative. But if you multiply the function outside by a, then it's absolute value of a times its tall on the x-axis and flipped upside down if a is negative. So those are your algebra techniques. Now you can apply them to these graphs. Don't worry, it's actually going to get eventually easier. I tell people sometimes I feel like a one-man band up here trying to do all this stuff. But pretty soon it gets a little easier. You can memorize some of this stuff. So here's an example. Let's apply it to the sine function. Sketch y equals 3 sine 2x. How can I sketch that? And by the way, I should make this note here. If I want to sketch y equals AF of bx, so I put a b inside the parentheses and an a outside. Now what happens? It does both, right? It does a vertical stretch absolute value of a and flips it upside down if a is negative. It does a horizontal stretch 1 over absolute value of b and flips it over the y-axis if b is negative. So this one, when you put them together, it does both. Now with that in tow, we can do this.
I can't see it down there.
Okay, let's see if I can. I'm showing a lot of room up here. Let's see. There we go. Is that better? I hope. Zooming out a little. Thank you. All right, so y equals 3 sine 2x. This is an a f of bx with f the sine wave instead of the square function. A equals 3 and b equals 2. So what's it going to do? This is a vertical stretch by a factor of 3 about the x-axis. With a horizontal stretch about the y-axis by a factor of 1 over 2. Absolute value is still 1 over 2. 1/2. No flips because they're both positive numbers. So I can sketch this immediately. and say, well, instead of going between y equals -1 and y equals 1, that's what it did before. If it's 3 times as tall, it's going to go between 3 and -3, right? If it's 3 times as tall, it's a wave going up and down. Furthermore, it's going to be switched half as far along this axis. So instead of repeating every 2 pi units, it's going to repeat every pi units. What I do is I draw the sine function, so it goes all the way up to here, all the way back down to the bottom down here, with the guidelines here, if you like, 3 times as tall. In the period, we say, when it repeats, instead of 2 pi, pi, because it's 1/2 as far, and it looks like that. And then it repeats this over and over. We say this is 1 period. Here's another. Every time it repeats 1 all the way to the top, all the way to the bottom, back to the middle, we call that 1 period of the sine wave. Oops. And at minus pi, it's do the same thing, just like that. So there it is. That maybe gives you an idea, right? To sketch this thing, all I really have to do, if you think about it, is relabel the axes. All I did was make these numbers 3 times as big and these numbers half as big and drew away, right? So in some sense, I'm just relabeling this. It's in order to accommodate the stretch. So that tells you this. We'll say easier. That's the reason. But easier to memorize and implement is to multiply the guidelines by the absolute value of A to accommodate the stretch, and change the period, the x length over which this repeats. It used to repeat every 2 pi radians. Now you change it to 2 pi over absolute value of b to accommodate that this graph is stretched by 1 over b. All right, and then do any flips. Flip horizontal. If b is less than 0, maybe we should do vertical first. So we vertical if a is less than 0. Horizontal if b is less than 0. And this leads to a graphing strategy. In general, we're going to only take graphs where b is greater than 0. To simplify this, we will only graph y equals a sine bx with b positive. Why would we do that? It's because we can always make it so. We'll say if b is less than 0, use the even odd properties to get the minus out. All right, so now we have our graphing strategy. This is the graphing strategy then. To sketch y equals a sine bx or y equals a cosine bx. 1, make b positive using an even or odd identity. you take the minus away. Once that's the case, sketch a wave sketch a sine or cosine. Cosine starting at the top, sine starting through the middle, as we showed, of amplitude. That's the height from the middle up to the top guideline in the middle down to the bottom guideline equals absolute value of A, distance from middle to top. And period equals 2 pi over B. There's nothing more than that. You just draw a wave that oscillates like the one we saw in the graph over there, that repeats every this many units and goes up and down between these two guidelines. That's it. And if B is less than 0, you get it out. And then finally, 3, flip upside down. You don't have to worry about the horizontal because you may be positive. So you flip upside down if A is negative. That's it. Now I don't have to be a one-man band. I just do these 3 things. We'll do an example. Are there any questions on what I wrote down? Let me repeat the last example, just with this in mind. So this is the big graphing strategy for A sine bx or A cosine bx. Y equals 3 sine 2x. What do? I say 1, B has already been greater than 0, so there's nothing to do. Two, I compute the amplitude for the guidelines. Absolute value of A, if I look at this, I see this is A and this is B. A is what multiplies outside, B is what multiplies inside. Amplitude of A is absolute value of 3 is 3. The period is absolute value of 2. The book will often leave out the absolute value on this one because they're just assuming that B is, you may be positive like we just suggested in step 1. So they may leave this out assuming that you did this. That's why. But in practice, it needs to be in there. So the period is 2. What am I saying? 2. 2 pi over B is 2 pi over absolute value of 2 is pi. So the period is pi. And then 3, there's no flip since A is positive. That's it. Now you can sketch it, right? You sketch your guidelines at plus or minus A, 1, 2, 3. 1, 2, 3. You start at the origin for the sine. The cosine starts at the top, the sine starts at the origin. Just go up and down and up and back to the middle. And this is 1 period, pi. Go up and down back to the middle like this. This must be minus pi is 1 period. And it keeps going forever, right? It's the song that never ends. You hear that when you're kid. So it goes on forever. In physics, actually, if you have something like this that just has this, you shoot it down, you jiggle a long string and you make a little thing like this, they call that a pulse. Physics, a wave is something that goes on forever. So that's a distinction they make. So this is a sine wave. When you do this, there it is for sine. You just do those 3 steps and it's real easy. Huh? Alcoholics can do the 3-step method. I say you guys can do it for trigonometry, right? So let's try another one. This time I want to use cosine. Suppose I want to sketch, this time y equals 4 cosine of minus a half x. How about that? I do the 3 steps, right? 1, y equals 4 cosine minus a half x. Oh, b is negative, so what do? Cosine is even, I can take the minus away, right? Cosine of minus theta, if I think of this as theta. Cosine of minus theta is same as cosine plus theta by the even property of cosine. I can just drop the minus. So all I really have to do is get 4 cosine plus 1/2 x, and now I can go to step 2. The amplitude for the waves, how high up and how high down from the middle, is absolute value of 4 this time. Is 4. The period, I'll write P for period, usually it's shorter, is 2 pi over absolute value of 1/2, and we can drop absolute value with these negatives, sometimes I'll just drop it. Be careful, 2 pi over 1/2, the 2's don't cancel, right? If you write these out as quotients, it's 2 pi over 1, all over 1/2, it's top times bottom over middle times middle, it's 2 times 2 pi over 1 times 1 is 4 pi. So they reinforce each other when one's a numerator and one's a denominator. Be careful, the period is 4 pi. And now 3, there's no flip, even though B is negative, because, right, I fixed it and changed it to graphing something that would be positive. And A is positive, so there's no vertical flip. No flip. You ignore the B because you made it positive. No vertical flip because A is positive. Now I can sketch it easy as that. However, cosine starts at the top, right? So I go 1, 2, 3, 4. That's the amplitude. Draw a guideline. You don't have to draw this, but it really helps me. Draw a guideline at y equals 4. Draw a guideline down here at y equals minus 4 if I left enough room. The period is 4 pi. So this is about 12. I'm not going to scale the axes the same. This is 4 pi. And similarly out here at minus 4 pi, I'll complete the period. And then the cosine starts at the top. So I'll put this point 0, 4 at the top guideline. Then I'll repeat it at the end of a period. 4 pi, pi. That's how you figure out the points. You say, it starts at this point, 1 period later, it's the same point. The cosine, you start at the top, draw it all the way down to the bottom, back to the middle, or back to the top. There's 1 period of the cosine, and then you repeat that over and over. You do the same thing here. I think I drew my minus 4 pi in the wrong spot. But at minus 4 pi, it also comes back to the top, and then it goes on forever, right? When you do that, that's what you got to do on this. 1, get B positive by using an even or odd property. Like here, I can just take it away since cosine is even. Find the guidelines, plus and minus absolute value of A. Find the period, so I draw one wave and it has to reach that point at a period. And then the part I didn't say is if there was a flip, then I have to turn this whole thing upside down. My cosine turned upside down and now starts at the bottom, goes up and back down here. So cosine starts at the top if A is positive, but if A is negative, then you have to do a flip at the end and go to the bottom. There's the graph of y equals 4 cosine minus 1/2 x. When I put a minus 1/2 in here, it actually doubled the period, right? Because of the horizontal stretch is 1 over 1/2, it's 2. That look okay? Let's try this one. Suppose I said sketch y equals minus 1/3 sine 2x. So it's an A sine dx, right? These are the 3 steps. I say 1, let's make it make B positive. B is already greater than 0. There's nothing to do. What about I do?
Wait a minute. Haven't we all? Oh, no. Never mind. Sorry.
Okay. If B had been negative, what would I do?
You just make it positive because
Yeah, sine is an odd function, so I pull it out and cancel this one. What I do. So if sine has a negative inside, you pull it out because sine is odd. If cosine has a negative inside, you just get rid of it because it's an even. So this one I didn't put a negative here, but had there been a minus, I just pull it out. All right. Now the second step, I say the amplitude is absolute value of A is a third, so the guidelines will be a plus and minus a third. The period is 2 pi over whatever B is. 2 pi over 2 is pi, so this will repeat every pi units. And then 3, this time I do flip upside down because A is negative. So there's the 3 steps. I don't have to do quite as many calisthenics with my hand. I just draw guidelines at plus and minus a third. So this is a wave that doesn't go real high or real low. Here's y equals a third. Here's y equals minus a third. The period is pi. So I'm going to go out here to pi. If I sketch these equally, then this should be about 9 times as long as this, right? This is a third, and this is about 3. Now the sine function then is a wave that starts at the origin and goes like this, but what am I needing to do still? So it should come back to pi. It starts at 0, 0. The sine always starts at 0, 0. It should repeat every pi unit, so I ought to get pi 0.
I have to flip it.
Yeah, the only thing I haven't flipped it. So this is what it would be unflipped. Flipped, I have to draw it down like that. It has to start down instead of up. And then it goes on forever. Now, one thing I haven't said in all these graphs that I do want you to do is this is kind of a rudimentary graph. I only have 2 points on it. What are some other points I can plot? On the next test, not on this one. This is chapter 6, and the test is only in chapter 5. But we can get 5 exact points on every period. We always know the starting point, right? Because the sine starts at the origin, the cosine starts at the top if A is positive, or at the bottom if A is negative. And then we draw the point at the end of the period with the same y coordinate, right? So we get 2 right off. Then we've got 3 intermediate points. What point is this? I'll let you guess. It looks symmetric. It's always the point halfway between these. So I just average the exponents. 0 to pi, halfway in between is pi over 2. And it crosses the x-axis there halfway in between. So pi over 2, 0, the point halfway in between, is always also in the midline here. And where do you think this point is? Looks of it, it looks halfway between pi over 2 and pi. And similarly, this point, halfway between 0 and pi over 2. And in fact, it is. In fact, if you do your trigonometry, you can figure it. But this is actually pi over 4, halfway between these 2 points. And this is 3 pi over 4, halfway between these 2 points. And if you do that halfway between these 2, halfway between those, and halfway between those, you always get 3 sequence. Now you get 1, 2, 3, 4, 5 that you plot exactly in every sine wave. Okay? So the graphing strategy, people look for this. Is it crossing in the right spot? Is it reaching the peak in the valley at the right point? That's what they look for. Those are the important points. So that's how you can sketch any sine and cosine. Do those 3 steps. Plot the 5 points exactly using that strategy, halfway in between and halfway in between. I think how much time I have here to, if I have enough time. Now, if that's not enough, we can do more. This is where I really like 50-minute classes better. You can go home and do the homework on this and come back and be expert for this next part, where the way it is, we're going to have to do 2 things at once. Also, from algebra, we can do one more thing. This is one more thing the engineers do. Most of their graphs are like that. You know, if you have a high frequency oscillation in your circuit, you know, the current is going real fast, and you just draw a high frequency. B in there is actually called the angular frequency. And it's related to frequency with a factor of 2 pi. But you increase B and it increases the oscillation frequency. It makes the period shorter. And if you want a louder signal, like for earthquake analysis, you use vibration analysis, then you make A bigger. And that's what happens in practice is they use sine waves with larger A's or B's or smaller A's or B's. But also we can sometimes need this from algebra. If you take y equals f of x minus a number A, how does that relate to a graph of y equals f of x? So it's great stuff in algebra. You always wondered what it's going to be used for, but it gets used now. The graph of y equals f of x minus a is just a graph of y equals f of x. Do what to it? Can you guess of that? Instead of stretched, it's
Shrinking.
yeah, shifted, yeah. Shifted by plus a, whatever you subtract. And y equals f of x plus b is the graph of y equals f of x. Shifted how? I should have said on this one horizontally by a. This one is shifted vertically by b. What does this do to y equals f of x? Right? It just adds b to every y coordinate, so it slides it up, right? You just add 2 to every y coordinate, moves up. This one, if you subtract it, then x only has to be a units less to get the same y, so that moves it over a, right? If it has to be a units less to get the same y, then you can, right? You move it over. Well, it used to be that f of 0 is some number, now f of 2 is that number, if a is 2, right? And then y equals f of x minus a plus b does both. It shifts it horizontally by a and vertically by b. That's everything we're going to need. Engineers and scientists who do all this wave analysis, they use stretching and shifting, and that's it, really. There are other ways people consider, but far and away, the sine waves are the important ones. So now we can sketch more general graphs. I guess I better put it up here. Consider that when the function is sine or cosine. To sketch more generally, so far we've just been talking about y equals a sine dx. I'm going to leave a little space this time. Right? Or y equals a cosine dx. I'll leave a little space this time. We found the amplitude, we found the period. Sine started at the middle, cosine started at the top. Easy, right? You just sketch a wave and do the right period and go between the guidelines. Now we're going to change the game. We're going to put minus c and plus d. I could put it on this way too. If I have x minus c, it's a shift by plus c in the graph. I add a d on the end. It's shifted vertically by d. Maybe I should have done that in the first place. Minus c in here and plus d out here is shifted horizontally by c, vertically by t. This graph is the stretch using a and b, and then the shift using c and d. And so we just have to do the same 3 steps as before, but first we do a shift to accommodate. We shift really the origin to the point CD, C horizontally and D vertically. Then proceed with your graphing strategy that you did before. You find the amplitude is absolute value of A. The period is 2 pi over B. And 3, you flip upside down if A is less than 0. And I forgot something, shoot. First you want to make B positive. So I put in a step 0, make B positive by an even odd identity. Assuming B is positive, then you can only have a vertical. I'm realizing I neglected to put up an example of that shifting. Here's an example, y equals x squared function, easy one from algebra. Just put it on the side here to go with the other notes. Suppose that y equals x squared. What is the graph of y equals x minus 1 squared plus 2? What does that do to my parabola here? This one has no stretch. It's just replace x by x minus c and then add d to the function, right? So this is your c and this is your d. It's the y equals x squared function. Replace x by x minus 1 and then add 2 at the end. This is a horizontal shift by 1. Vertical shift by 2. So you take the point 0, 0, and it goes to the point 1, 2, and you do a parabola that's exactly the same shape. Translate it. So this used to be 1, 1. It's 1 unit over, 1 unit up. This one too, move it over 1 and up 1, and you get the point 2, 3. This one is 1 left and 1 up. This one is 1 left and 1 up. You got 2, 0, 3. And this is a shift or a translation. There is no stretch. It's exactly the same shape here. So that was the idea of the shifts. If you place x by x minus the number, it shifts it this way. And let me do one intermediate step here too. This is y equals x squared. What is y equals x minus 1 squared? I just replace x by x minus 1. It moves the graph over 1. It's exactly the same shape right here. When x is 1, you square 0, just like when you put x equals 0 here. Right? Put x equals 2, you square 1 like you did here. So you get the point here, 1, 0, 2, 1, because you have to move the graph you have to move 1 unit right to square the same number you did here. And so this one shifts at 1 right. If you shift at 1 right and 2 up, this adds 2 to every y coordinate, then you get this graph. Same shape as that one. And that's what we're saying here, is if you have one of these kind of graphs, putting a plus d in the end just moves the whole graph up by d, and it's replacing, and I need to put it like this, dx minus c. Just a little more complicated than I'm letting on here. This is why I had a here. I'll rewrite this. Sorry, but I want to make sure it's right the first time. I want to use their same notation. I'm going to have to, if I have y equals a sine bx minus c plus d, right? Here's what I do. 0, make b greater than 0 by an even and odd property. You can get a corresponding function to the graph where b is positive. All right. Now, shift the origin in this notation is to c over b t, because you rewrite this as A sine B times X minus C over B plus D, right? Or A cosine B X minus C over B plus D. You don't have to rewrite this. I rewrite this to show you that if you rewrite it like this, what you can see is that we take the function y equals A sine bx, replace x by x minus c over b and add a d on the end. So actually c over b is the shift, right? If you replace x with parentheses, x minus c over b, then c over b is the shift. So if you have bx minus c in here, you're thinking of writing it like this, but you don't have to. You observe that the shift is always c over b. The d on the outside means the vertical shift is d. And so it's the graph of y equals a sine bx shifted by c over b and d. All right. So there's the shift, the origin to that point. Now, use your amplitude is absolute value of a. The period is 2 pi over b. Flip vertically if a happens to be negative. Otherwise, leave it alone. And you sketch the wave from the shift point. So as you can see, this is considerably more complicated. It's better to do the other one first, but it's actually just the same thing, shifted. You do exactly the same graph you did it before, a sine bx or a cosine bx, but just shift it. So instead of putting it at the origin, you put it at this point c over bd, and you just memorize that. You memorize this strategy from those kilographs of these cases, and you never have to write this down. I put this down to show you the derivation of this, that the shift point is c over bd by rewriting it like this, but you just leave it in this form in practice. Here's the example. Suppose I wanted to sketch y equals 2 sine 1/2 x minus pi over 3 plus 2. What does that look like? Identify the letters. A is on the outside multiplying. B is whatever multiplies x. C is whatever is subtracted, so C is plus pi over 3, right? And D is what's ever added on the end. So be careful, C is what's subtracted. From that, I just do these 4 steps, starting with 0. I make B positive. Well, step 0, B is already positive, so there's nothing to do there. I don't need even or odd problem. Now the second one, I shift the graph to the point C over B, 0, D. Shift point C over BD. I just read it off. It's pi over 3 over 1/2. 2. Now being careful with your quotients. Top times bottom over middle times middle is 2 pi over 3. 2. There's the shift point. So instead of starting the sine graph at the origin, I'm going to start at this point. It's just the same graph as before, but shifted. Now I'm going to say the amplitude is still the absolute value of A, is absolute value of 2, is 2. The period is 2 pi over B. 2 pi over 1/2 is 4 pi. And then there's no flip since A is positive. Okay. So now I can sketch that more complicated graph. I do the same thing as before plus a shift. So I start at the point 2 pi over 3, 2. Here's 2. And here's 2 pi over 3. I didn't necessarily scale the axes the same. There's the shift point. What I do is I have a midline here instead of the x-axis, and I draw the guidelines plus or minus the amplitude 2 up above and below. So I go 2 more to 4, and I draw a guideline right here, y equals 4, 2 units above the midline, and 2 units down at y equals 0. So same thing as before, I just shift what was the origin over to here. Now, that's the amplitude. The period is 4 pi. Oh boy, I haven't left enough room. I want to make this look sort of scaled, right? So if there's the shift point, then I go over here. And if it's got period 4 pi, then what's this point where it completes one period? It's this point where it started, 2 pi over 3, the shifted x coordinate, plus 4 pi. So it's 4 pi units over, and it's a sine wave, so it goes up to the top, back down to the bottom, back to the middle. Exactly the same thing you do before, it's just starts here instead of at the origin, that's it. Take the point, C over B, D, start there. Guideline, absolute value of A up, absolute value of A down. There it is. Then you repeat that over and over forever, right? This point here would be 2 pi over 3 minus 4 pi. One period to the left. So, not only that, we can get exact points. What is this point here? You have to do your quotients, right? Put them over a common denominator. 2 pi over 3 plus 12 pi over 3, multiplying top and bottom by 3, is 14 pi over 3. That's this point. So I have a point here, an exact point, 14 pi over 3. Same y coordinate as this. The shift point was 2 pi over 3, 2. That's the shift point. This must be 14 pi over 3, 2. The same y coordinate, right? Because it completed a period. Halfway between, what's halfway between 2 and 14? 8, right? These are 12 apart, so you go 6 over. This must be 8 pi over 3. 2 halfway between. Halfway between 2 pi over 3 and 14 pi over 3. Halfway between 2 pi over 3 and 8 pi over 3. Halfway between 2 and 8 is 5, right? So put 5 pi over 3. Halfway between 8 and 14 is 11. 11 pi over 3. I can get 5 exact points. It reaches the top 4 here. Wrote it poorly. At 5 pi over 3, so I got the point 5 pi over 3, 4, 11 pi over 3, 0. One, 2, 3, 4, 5 exact points. And a wave that repeats forever. That's everything. Everything you need to graph sine and cosine. And all the engineers can do all this stuff. Any questions on that? Just a 5-step strategy instead of a 3-step strategy. Or I guess technically it is 4-step strategy. I call it 5 because it's 2 shifts, one in horizontal and one vertical, but it's just the 3 steps of 4 plus a shift. Let's try cosine. Cosine is the hardest one. I think I have time. Yeah. One last graph and we'll end at a good point. Some questions next time. Let's sketch this one. This will be the hardest one. Y equals minus 3 cosine 2 pi over 3x minus pi over 6. How about that? Oh, yeah. Let's say plus 1, sorry. Let's sketch that. It's the same 4 steps, right? Here's A, whatever multiplies the sine or cosine. Here's B, whatever multiplies x. Here's C, whatever is subtracted. Here's D, whatever's added on to everything. Right? So step 0 is to check that b is greater than 0, and if not, then use an even or odd property to fix it. Step 1 is I do the shift point. What's the shift point? You just memorize it. It's C over BD. Right? You just memorize that. Otherwise, you have to figure out algebra every time, which I told you that just makes me dizzy. C over B is pi over 6 over 2 pi over 3. And so you get some fast fractions here. And then D is 1. Well, what's this? Top times bottom is 3 pi. Middle times middle is 12 pi. It's that. It is 1/4. The pi's cancel this case. 1. So this time, because I have a pi in my b, I actually get a number without pi in it for the shift point. And put it over here. I'll go to the shift point 1/4, 1. And then I just do the other steps. What's the period? What's the amplitude? So I draw my guidelines. Its absolute value of A is 3. Right? A is -3, so its absolute value is +3. Amplitude is always positive, right? A can be plus or minus, but the amplitude is absolute value of A is always positive. The period is always 2 pi over B. See, this is what you memorize. You memorize the shift point, C over BD. Amplitude is absolute value of A. Period is 2 pi over B. And flip it is A is negative. And that's it. You just have to memorize that, and then you don't have so much difficult algebra. 2 pi over B is 2 pi over 2 pi over 3. And this is a trick here, right? I've got a non-fraction over a fraction. Well, quotient. Non-quotient over a quotient. Fractions are supposed to be, right, integers over integers. No pi's in them. How do I do that? I write 2 pi as 2 pi over 1. All over 2 pi over 3. Now I can take top times bottom. 3 times 2 pi over middle times middle. 1 times 2 pi. And the pi's cancel, luckily, and the 2's cancel. It's 3. So this has period 3 without a pi in it, again, because B had a pi in it. There's the amplitude and period. Then I'll flip. If A is less than 0. No flip, since A is positive.
Actually, it's negative.
Oh, I'm sorry, it is, yeah. Yeah, thank you. I did that on purpose, I forgot for a second, thank you. Yeah, flip yes, because A is less than 0. That was one of the points of this one, actually. And then it's a cosine, so it doesn't start at the middle, it starts at the top, and when it's flipped, it starts at the bottom. So here's what I do. I plot the shift point, 1/4, 1. I go up 3 units to the top guideline. Ooh, let's see. 1, 2, 3, 4. Right, 3 units up to the top guideline. There's the midline. You can graph that if you want. 3 units down, 0, -1, -2 is the bottom guideline. The period is 3. So I'm going to get another point out here at 3 plus a quarter, which is 12 quarters plus a quarter is 13/4. So I get the point 13/4 one to go with the point 1/4 one, exactly 3 units apart, right? So draw the shift point, draw the guidelines, 3 units up and 3 units down. That's the amplitude. This one, the period is 3 also, so we go over 3 units this way. Now we can get 5 exact points. Halfway between 1/4 and 13/4 is what? Well, they're 12/4 apart, so half of that would be 6/4, or 300. So it's like 7/4. Halfway between 1/4 and 13/4 is 7/4. So I guess 7 is halfway between 1 and 13. Halfway between 1 and 7 is 4, so you got 4/4. Halfway between 7 and 13 is 10, so you got 10/4. And you can reduce these. 10/4 is 5 halves. 4/4 is 1. All right. So now we've got a cosine. We have to start at the bottom guideline. flipped cosine, we start at the bottom guideline and finish at the bottom guideline. And so we've got this, here's the points on the graph, 1/4 minus 2, 13/4 minus 2. The height, it has to go up, cross the midline at this, let's see, I'm sorry. Cross the midline halfway between these at this point. This is the point 1, 1, because it has to be on the midline halfway between these 2 points. Then go up to the top at the point halfway in between, I get the point 7/4, 4. Then down across the midline at this point here, 5/2. I have 5/2, 1. Back down to the bottom to complete 1 period and 3 units. 1, 2, 3, 4, 5 exact points. There it is, and then the wave goes on forever, right? So there's the hard one. This is the graph of y equals 3 cosine 2 pi over 3x minus pi over 6 plus 1. That's its graph. Any graph whatsoever, y equals a sine or cosine, bx minus c plus d, you can now sketch by this strategy. And that's what people need in practice. All right, so I'm just about out of time then. I think, let me not assign the homework on this, even though, go ahead and work it. I'm going to give you most of the problems out of 6.1. But instead, I'm going to say, look at the review sheet on chapter 5. This is all chapter 6, won't be on the exam. Bring some questions for next time on chapter 5. As soon as you take your test on Tuesday, this homework will be due. I'd like you to do this. Any questions on this one? Does it make sense? Hope. Find the shift point. You memorize C over BD. Find the amplitude. Its absolute value of A, and go up and down the amplitude and sketch the guidelines. Find the period. It's always 2 pi over B, and you move over B from the shift point. And you draw a wave from the bottom guide between the bottom and top guidelines. Sine starting at the middle, cosine starting at the top and bottom. That's it. Okay. Thank you for coming and giving me good questions. Appreciate it. See you on Thursday, and mostly we'll do review. We might go a little further with this. But that ends the section, actually. You can do all the problems in there now.
Thanks, Professor. Have a good one.
Thank you. Have a good day.
Thank you.
Yeah, thank you.